Hello students, in this video we'll show how to find the Laplace transform of a periodic function. Let's suppose that f maps 0 infinity into R is periodic.
What's that?
What that means that f of t plus p is equal to f of t for some p called the period. So here p is called the period. Okay. So now let's find the Laplace transform of this thing. So by definition, f tilde of s for this periodic function is going to be the integral from 0 to infinity of f of t e to the negative st dt. Okay? And so what I'm going to do now is I'm going to write this integral many times. I'm going to write this as the integral from 0 to p of f of t e to the negative st dt plus the integral from p to 2p of f of t e to the negative st dt, and so on forever, right? So I'm going to integrate it over the period over and over and over and over again. So if I write this as an infinite series, what is this? This is the sum. N goes from 0 to infinity. The integral from np to n plus 1 p. Let's check. When n is equal to 0, I go from 0 to p. When n is equal to 1, I go from p to 2p, etc. So this works. Of f of t e to the negative st dt. Good? And so now what I'm going to do on these intervals is that I'm going to shift this function over here. So what I'm going to do is I'm going to consider on this interval over here, I'm going to let t be tau plus np. Okay? And so let's think what happens if I make this substitution over here. I make the substitution, I'm going to replace f of t with tau plus np. I'm going to replace this e to the negative st with tau plus np. And of course, dt and d tau are the same because n and p are constants. And now what happens over here? So when t is equal to np, that's tau equals 0. So t equals np is the same as tau being equal to 0. And when t is equal to np plus p, that corresponds to the top limit. That corresponds to tau being equal to p. Tau equals p. Okay? So if we change our limits by this change of coordinate, what do we have? We have the sum. N goes from 0 to infinity of the integral from 0 to p. And then we have an f of this tau plus np. F of tau plus np. And then e to the negative s, e to the negative s. And then, of course, tau plus np, tau plus np. And then I have a d tau. Great. Now, the beautiful thing is that since f is periodic, I've just shifted f over by n copies of its period. So if I apply this result again, I have f of t plus 2p is f of t plus p, which is f of t again. So these things, this is just really nothing more than just f of tau. So this is just f of tau by periodicity. Great. And so now I have an e to the negative s np, so I'm going to write this in the following way. This is the sum. N goes from 0 to infinity. This e to the negative s np does not depend on tau. I can pull that out. That's e to the negative s np. And then the integral from 0 to p of f of tau, and then e to the negative s tau d tau. There's no n's in this expression over here, and this is just a geometric progression over here, right? So with the common factor of e to the negative s p, right? And so this is a geometric series. And so what this is going to be equal to the integral from 0 up to p of f of tau e to the negative s tau d tau, okay? Divided by, if I sum up this series, and if we recall the sum, n goes from 0 to infinity of r to the power n is just 1 over 1 minus r, provided that r is less than 1 in absolute value, which e to the negative s np is, certainly if s is greater than 0. And so what we have over here is going to be divided by 1 minus e to the negative s times p over here. Beautiful. And so this is the formula for the Laplace transform of a periodic function. So let's see an example of this. And the most classic example is the example of the Haar function. So I'm going to write down what a Haar function is. Here's our classic Haar function. Our Haar function is just going to be equal to 1 if t is between 0 and the value c. It's going to be negative 1 if t is between c and 2c. And I'm going to make this periodic. So this is our function h of t. And I'm going to set h of t plus 2c to be equal to h of t. So I make it periodic with period 2c. So in this problem, my p is equal to 2c. So all I have to do is do this integral on top over here. So what's the Laplace transform of this periodized function? So the Laplace transform h tilde of s of this Haar function is going to be, well, it's going to be the integral from 0 to 2c of our function h of t, e to the negative st dt, divided by 1 minus, and then I have an e to the negative s, e to the negative 2cs, okay? Now, what's this Haar function going to integrate to? So, of course, I'm going to integrate from 0 to c. So it's just going to be an e to the negative st. So the first thing this is going to give me is this is going to give me an e to the negative st over negative s from 0 up to c. That's from 0 to 1. I should have a 1 over there. And then I'm going to have a negative 1, so that's going to be a positive e to the negative st over s from c to 2c. All right? All divided by 1 minus e to the negative 2cs. Great. Now, of course, the bottom one over here is going to be the positive 1, so everything's going to have a factor of 1 over s. So let's just figure out what happens with the e to the negative c. So this is going to be a 1 over s, 1 minus e to the negative 2cs. And then what? So when I plug in the top limit is going to be just a negative, first thing is going to be a negative e to the negative sc. The bottom is going to be positive. It's going to be a positive 1 plus 1. Okay? And then over here, the top limit is going to be positive. It's going to be a plus e to the negative s times 2c. And then the bottom is going to be negative. It's going to be a negative e to the negative e to the negative sc. Okay?
Okay.
And then what do we see over here? And then this will simplify. And if we just put all this together, this will simplify to something nice we're going to in terms of inverse tangent. Let's just leave it like this since we're sort of running out of space and we don't want to keep having to symmetrize this thing over here. So this is going to be the inverse, and this is going to be the Laplace transform of this Haar function that's periodized. But the important thing to remember is that all you have to do is integrate over the period, the function times e to the negative st, and divide by this exponential factor over here to find the Laplace transform of a periodic function. Thank you very much.